Welcome to Scale Your Game's Core Backend Beyond Viral Levels. My name is Vlad Vlasceanu. I am a Database Specialist Solutions Architect with AWS. And today's session will focus on the part of the gaming architecture that's really the hardest to scale, which is the data tier. To set expectations, this is a deeper dive. We expect the audience to be familiar with core AWS concepts and we will not focus on application scaling. Those are generally stateless services, but instead on the data tier, the stateful services. So how do we deploy an effective data tier to support the needs of the most demanding game? It's really easy. You use the right tool for the right job. And AWS offers a wide variety of database services. It has both deep and broad portfolio, but we generally like to classify them under relational and non-relational databases. So you have, for example, Amazon Aurora, which is a high throughput, high concurrency relational database, and Amazon RDS, which provides you with the ability to spin up commercial or open source database engines and operating in a managed service environment. We also have non-relational database services, the NoSQL types databases, Amazon Dynamodb, which is a really high throughput and high performance key value store or document store, Amazon Neptune, which is a graph database, Amazon Elasticache, which provides in-memory data storage services. And along with these services, we have a collection of tools and services that are really meant to make developing database applications easier. We have services that allow you to move data easily. We have services that integrate with our database services, such as Amazon S3, where you can export and import data between your database and Amazon S3, or we use that for backups as well. You have Aws Lambda, which our database services can invoke Lambda functions. So all sorts of integrations that are enriching the ecosystem and the types of workloads and use cases that we can run with databases. All of these services have a few things in common. Like I mentioned, they are managed services, where AWS takes care of the day-to-day operation of the physical infrastructure, securing the physical infrastructure, backing up and patching these databases, providing the hardware resiliency. So you, as a customer, can just focus on the things that really bring value to your business, which is implementing the workloads and tuning those workloads in such a way so you can achieve the desired levels of scale. And all of these services are accessible via APIs. You can spin up an entire database cluster with a few simple API commands. They also have one thing that is not in common. They are all fit for specific use cases. They're built and optimized to do certain types of data interactions really well. And the AWS platform is the reason why the largest and fastest growing gaming companies pick AWS. When you picture a generic gaming workload and the services that are typically critical components in every game that we encounter, they really can be supported by 4 key database services. And we'll focus a little bit deeper on them in the rest of this presentation. They are Amazon Aurora, Amazon Dynamodb, Amazon Elasticache, specifically the version for Redis, and Amazon Neptune. So how do you pick the right database service for your workload? Over time, we've kind of boiled it down to 10 considerations or types of considerations that come into play. And some of them are really obvious, like the shape of your data or the size of your data set or the types and volume of queries that you're running against your database. But there are other considerations that may be less straightforward. For example, the level of expertise in your organization. Which database engines do you are you more experienced with? Getting deep expertise in a new database engine and developing those skills doesn't happen overnight, so there's a cost associated to that. There's business concerns and potentially even legacy concerns that may influence the decision. And all in all told, there's also very wide degree of overlap. You might be in a situation where more than one database service may indeed meet your requirements. So we call this a gray area. And in that case, cost becomes a differentiator. You would pick the service that gives you the best cost optimization. Now I'll give you an example. Game state, is a type of semi-structured data. If you can picture the game state, essentially tracking the progress of a player throughout the game, throughout the campaigns, throughout the levels of a game, depending on how the game is structured. So that data evolves as the user proceeds and plays the game. It's a natural data structure to fit in Amazon DynamoDB because it fits really well into that document store model. And indeed, a lot of customers use DynamoDB to store game state data at scale. And yet we have customers that also like to model that game state in a relational database. You basically take a table with a couple of different key columns, and then you have a large blob or a JSON structure that contains your actual state information. And for those customers, they arrive at the conclusion that Aurora might be the more cost-effective option for their particular size of those game state records and the level of performance that they need and the level of concurrency they need. So the optimal solution really comes from extensive testing at the anticipated scale of your game. So how do we build an effective gaming backend on top of AWS data services? And let's start with a generic architecture. And when we're looking at the generic architecture for a game, and this is something that we see commonly with a lot of customers in the gaming spaces, you typically start with the application layer. The application layer is a collection of stateless services. Microservices architectures are not uncommon. But the way they are implemented matters less than the fact that they can be horizontally scaled based on demand. You can use many things to actually implement that. For example, you might use Amazon EC2 instances with auto-scaling groups, and those can scale on demand based. A lot of customers use containerized workloads provided, for example, by Amazon ECS or Elastic Container Service or Amazon EKS or Elastic Kubernetes Service. Some customers use serverless architectures using Lambda and API Gateway. And other customers use dedicated gaming services like Amazon GameSparks. And in reality, many customers use more than one of these solutions. They might have a mix of that. But around this microservice architectures, collection of microservices, you have a collection of data services that are dedicated for specific use cases. You might have a data persistence layer where you're storing your game state, where you're storing player profiles. You might be storing their purchases and inventory and all sorts of other data. You will have a caching layer in front of that data persistence layer because predominantly gaming workloads are read heavy. So it makes sense to cache some of that information in memory. You will have most likely a chat and messaging infrastructure so that the players can interact with each other as they're playing your games. And you're going to have a leaderboards and game statistics workload or service to provide that type of information and feedback to your players and rankings. All of these services can use different data services. And they typically play on the strengths of those solutions in relation to the use case. So what about data persistence? There's different types of data structures and access patterns that kind of come into play at your data persistence layers. So we usually see multiple services used at scale to take advantage of their capabilities and their optimizations that they have in those database engines. So you might have, for example, Amazon Aurora for more transactional, more relational data such as purchases or inventory. You might use Amazon Dynamodb to store player profiles or other game metadata. And we've already mentioned game state as being a type of data that might fit well in either Aurora or Dynamodb. And you might have even other types of data that might be better suited for other database engines, such as Elasticsearch if it's game search type workload. And Amazon Aurora is a great fit for gaming workloads because we took essentially the traditional monolithic database engine and broke it apart. We've built a decoupled infrastructure where we've decoupled compute from storage. So now Amazon Aurora provides a purpose-built, log-structured, highly distributed storage service that can scale as your data set grows. And it also provides a very high degree of durability. We store 6 copies of your data across 3 availability zones in a region. So this is a very, very fault-tolerant architecture at the storage system. And we also provide you with capabilities for continuous backups and integrations with other AWS services that generally help you make developing applications easier using our platform. And as a result, we see Aurora having the performance and availability comparable and even exceeding that of commercial databases. And we're achieving that with open source database engines. And Aurora is also a drop-in replacement for MySQL or Postgres type databases because it is wire protocol compatible with those. So you can take your traditional MySQL database and replace it with Amazon Aurora, and you don't actually have to make any significant application changes. And of course, Aurora provides a simple pay-as-you-go model where you pay for the compute capacity that you're consuming, and you're also paying for the amount of storage that you're consuming, only when you're actually consuming those resources. Now, that said, there are a number of features that are particularly compelling for gaming workloads. Let me explain a little bit. Gaming workloads are overwhelmingly read-heavy, even when we factor in caching. So we've built this log-structured distributed storage layer that is actually shared between all of the nodes within an Aurora cluster. So you get reduced lag read replicas because they're doing less work. In a traditional database, your read replicas actually have to replicate logically all of the statements that are occurring on that principal, on that master database. And not so in Aurora. Aurora, because the storage is shared with all of the nodes, they already have access to all of the most up-to-date data. So it's just a matter of informing the database and keeping the page cache in sync and up to date with all the changes that are happening on the master. So the readers are doing fundamentally less work. And because of this decoupling between compute and storage, we can now also auto-scale the fleet of read replicas, so you can adjust the amount of read capacity available based on demand. Unlike MySQL Community Edition, for example, Amazon Aurora provides an adaptive thread pool, which allows us to handle large numbers of concurrent requests more efficiently. And I already mentioned storage is shared and scales with your data set, so you don't need to provision it. Now, another characteristic of the distributed nature of this storage service is that your volumes data is spread out over potentially tens or even hundreds of storage nodes, which provide you with a lot of parallel throughput capabilities at the storage layer. So your storage itself, your storage layer, is unlikely to actually ever be a bottleneck. It also provides built-in encryption capabilities as well, so you manage the data of your users in a secure way. And because we've decoupled compute from storage, the compute capacity is also scalable up or down with minimal disruption. So you can adjust the amount of compute capacity and memory and network throughput for a database instance based on your actual usage and based on your actual needs, independent of the actual storage of your cluster. But what if you don't even have to do that? So recently we launched Aurora Serverless, which is perfect for highly variable workloads, such as growing games or dev and test workloads for a game developer. Here's how it works. Your application doesn't connect directly to the database engine. Instead, we have a request router service, which is highly available and highly resilient, that acts as an intermediary, acts as a proxy between the two. And we also have a warm pool of compute instances, a warm pool of capacity that we can easily use to swap out your compute node that is running your database queries in Aurora Serverless. So for example, as your database load increases, we will go behind the scenes and replace the smaller compute node that was running your database before with a larger one. And we do this completely transparently. Your application connections never get disrupted. They are kept open by the request router, and any sort of queries that are issued while that scaling operation happens simply get queued up at the request router layer. So all you see from your application side is a slight increase in latency during the scaling operation. And a scaling operation takes about 5 seconds. Of course, we can do the same thing if your load suddenly decreases. We're going to swap out smaller compute capacity instead of the larger one. And with Aurora Serverless, you only pay for the amount of resources that you consume at any given point in time. So we have the concept of an Aurora capacity unit, which is roughly the equivalent of 2 gigabytes of RAM, and the associated amount of compute and networking capabilities. And we use that as a metric for billing purposes. So every second we measure how many Aurora capacity units your database is consuming, and we will charge you based on that number. So at any given point in time, you're only paying for the amount of compute capacity that you're actually using. And if you don't operate a database for some time, for example, a development workload, you simply scale down all the way to 0, and you stop paying for the compute capacity. So you can see how Aurora's features provide a highly scalable environment for structured and semi-structured data workloads. Now, what about NoSQL? For NoSQL type workloads, we offer Amazon DynamoDB. That service is great when your access patterns are very well defined, such as the example I had before with GameState, or for example, your player profiles where the interaction patterns are getting the player profile, updating a player profile. Amazon DynamoDB is a serverless offering. This means that you simply use our APIs and create a table. And then you tell us the throughput you need for that table in terms of read and write capacity. And then we use that information to allocate enough compute capacity behind the scenes to provide you with consistent low latency, single-digit millisecond latency, regardless of the size of that table. Dynamodb is also a very highly available service. In fact, for first in the industry, we're offering a 5 nines SLA for the global tables configuration of Dynamodb, which reflects our confidence in the reliability of this service. And just to give you an idea of, kind of scale of workloads that are running on Dynamodb, Amazon Retail is using Dynamodb for their shopping cart. And at Prime Day, it was able to scale to handle millions of users. We have customers using hundreds of terabytes or millions of operations per second with Dynamodb. So it's really designed as a service for mission-critical workloads that need no downtime and no data loss. Now, I already briefly mentioned it. There's a particularly compelling feature in Dynamodb called global tables. This is a fully automated replication feature that allows you to create tables that are replicated with each other across your choice of AWS regions. It is a first fully managed multi-master, multi-region database. And this is honestly great for games, especially games that are globally available, where you have players across the world interacting and playing the same games with each other. Because it allows you to have low latency reads and writes to locally available tables, minimizing the latency between those players and your data stores, while at the same time providing a layer where the data is fully replicated across all of the different regions where you might be operating that table. So it's critical for games where reducing lag is really critical to their success. And Dynamodb Global Tables also allows the database to stay available even in the event of a complete regional outage. You still have the data available and operational in the other region. Now, of course, typically if there's a region-wide failover, you probably also want to failover your application services to a different region, not just a data tier. But your database generally will remain available. And Dynamodb Global Tables offers an automatic resolution of concurrency conflicts. And it's really easy to set up with just a simple couple of simple clicks. You specify the regions where you want that table replicated, and we will handle all of the management and monitoring for you. Now, going back to our gaming architecture that I showed you earlier, what about the other components like chat and messaging? Chat, for example, is a critical workload for player experience. And it really allows communication between players in a session or friends in a game that really builds that community aspect in a game. And for that, we see customers use Amazon Elasticache for Redis, which is a managed service for the Redis in-memory data structure store, which is commonly used either as a data store or a cache or a message broker. And it's really the latter capability that makes it so powerful in gaming workloads. Redis has a pub/sub capability, and you can leverage that it's really easy to adopt, and you simply start defining a channel whenever, say, a session starts in your game and you have multiple players connecting with each other. And the client applications of all those players will then subscribe to that channel, and they can start sending and receiving messages. Some example commands to actually do that are shown on the slides. Now, key to understand is that message data is not persisted in Redis. But that's generally okay in gaming workloads. It's okay when a portion of a conversation is lost because it can either be retyped by the user, or, a lot of the gaming workloads that we see actually have an archival feature where a game developer collects those messages anyway for other applications and other reasons. They might have an archival service to store those messages, or they might use that for analytics or sentiment analysis. Now, to be sure, Elasticache for Redis is not a good choice if you need critical messaging where you cannot afford to lose messages. But in many, many gaming workloads, we see Elasticache used very effectively at scale. Now, there is a good practice to separate the chat cluster from all of your other Redis workloads. That way, your chat communication is not going to block or influence the performance of, say, other workloads like leaderboards or caching. And it allows those systems to scale independently as well based on their demand, and it also helps you reduce blast radius. Most gaming companies use Redis also for leaderboard. Redis has a dedicated data structure called a sorted set. And what that data structure does is, on insertion, Redis actually injects the records in the proper order, so that on retrieval, it's already sorted, removing some of the processing that overall happens. So, when we're going back to my statement previously where we said that gaming workloads are typically read heavy, it's much more efficient to do the sorting on insert than on read when you have to read that thousands of times. And because the in-memory retrieval is really, really fast, Redis becomes a really good place to store any sort of game statistics or leaderboards. And the leaderboard effectively in Redis essentially just, you just basically store a numeric value and tell Redis to sort the data based on it. The command that you would use in that case is zadd, and it's used to add a member to the sorted set. It's a simple single-line command, and that's really the power of Redis. It helps you simplify your application logic because it can accomplish a lot of different things with simple single-line commands. And like with the pub/sub example before, it's good to have a dedicated cluster for leaderboards as well. Another use case for Redis is helping you reduce the pressure on the backend data stores, on the persistence layer. And that's really, really key to handling scale as well. And the simplest architecture to use in that case is using a flat cache in front of your actual data persistence services. So say, for example, you're using Amazon Aurora, and you're using SQL queries to retrieve data sets out of Aurora. Then in Redis, what you would effectively do is you'll take the SQL statement, hash it, and use that as a hash key with the value stored as the result. And then you can easily retrieve that data set directly from memory. And it works really, really well because the query patterns in gaming workloads are read heavy. And it's often more cost effective to put a cache in front than to scale out the data persistence layer itself. But some customers in a gaming space go a step further than that and aggregate data received from different backends into a single Redis collection. So let's see how this works. So here's an example. Imagine that you have player purchases and their badges stored in Aurora, somewhat of a relational workload. And then the game state and the player profiles are stored in Dynamodb. As you start caching the data, you create a hash map in Redis that is associated potentially with the player, right? And then you store the different properties associated with that hash key that are coming from the different data stores and that you're receiving from the different backend engines. And you use the backend data stores to actually hydrate your cache rather than going through your application layer. And then you can select all or just a portion of the properties that you need. So basically how this works is, if you're looking on this diagram on the slide, is you might have Aurora and you're leveraging, for example, Lambda functions to stream out changes. And you can do that really easily because Aurora allows you to invoke a Lambda function. And you can package that invocation into a trigger on a table. When data changes in the table, a trigger gets fired, and a Lambda function gets executed, exporting the changes out and updating your Elastic Cache for Redis cluster. Or you can do that from DynamoDB using DynamoDB streams, which is a capability that allows you to stream changes out of your database, and again, invoke Lambda function or use other types of consumers to simply update the data in Elastic Cache the same way. So customers treat Redis as an aggregate cache and write back to it from changes in the data stores themselves, but they do that on the back end of their architecture, not through their application layer. So using these database services and scaling their layers, you can operate a gaming backend that can handle any of your game scale. And everything will be fine as long as load is stable. But of course, that's not always true. So once you start introducing variability, you'll see heavy pressure against various components of your backend solution. Your cache might not be enough or might not be big enough to handle the load, and it in turn will send pressure down to the persistence layer. And when that happens, you got a couple of options. You can add read replicas to your Aurora databases if you're using them, or you can leverage auto-scaling to automatically scale the number of read replicas of your Aurora database. Or if you're using serverless, you just let it scale up. If you're using DynamoDB, you can add throughput to your DynamoDB tables or leverage DynamoDB's auto-scaling capabilities to automatically add throughput capacity to those tables when the load against those tables increases. And you can scale up your Elastic Cache cluster with additional shards to absorb that pressure as well. Elastic Cache has an online sharding solution where you can simply change the configuration and the number of shards in your cluster without any disruption to the workloads. You don't lose any writes, but you might see a slight increase in latency. And in reality, customers will likely apply more than one of these options. You're probably going to expand your cache, and you're going to also scale out your data persistence layers. But auto-scaling isn't instant, and it takes time to actually provision additional resources. So it won't always help if your load spikes are beyond viral. So you need to supplement those capabilities with game-specific predictive metrics. Ask yourself this question: can you anticipate spikes in any way? Perhaps you're going to discover that there's a correlation between your spikes and marketing activities. There's a new advertising campaign going out and you're expecting a lot of new game players. You can use that to scale your infrastructure, or you might have what we call Canary Services. These are services that can inform you or give you a clue that there's about to be a spike. Simple example is your account management service or your login service, right? If more users start logging in, the chances are they're going to start playing the game. So you can use that information to start scaling up the infrastructure. Or a marketplace, if suddenly there's more players purchasing upgrades, or there's more new players purchasing your game, you can use that information to actually make scaling decisions. So the second question that you would need to ask is, can you distill those examples and those types of metrics into something that's useful, that you can use for auto-scaling or to make decisions to scale up manually? And in most cases, we find that customers actually have good opportunities to do that. But you got to watch out for your application's tolerance to latency variability. Here's a situation that we commonly see with different workloads, especially at high scale and performance levels. You might have, a database query. You're asking for some data about a player, perhaps, and you're expecting an answer within 50 milliseconds. The number doesn't really matter as much, but you have a defined period of time. And then if you're not getting that answer back, then the application starts aggressively retrying. This is a really, really bad practice because you will have variability in your latency and your response times during those scaling operations. So you want to make sure that the applications can tolerate that they don't overwhelm the databases or your data tiers during those and add additional load and additional risk to your architecture whenever scaling operations happen. And consequently, if you're sending more artificial load to your database, you might also make the wrong types of scaling decisions. So another topic I'd like to discuss is how do we go beyond scaling your workload and into scaling the reach of your games? Gaming is a natural environment for highly connected data. There's relationships between your players. There's a relationship between the games and the players. There's relationships between the different activities that they're performing in those games. This is very, very valuable data, and we see game developers tap into it increasingly more effectively. You can use a graph database to understand the relationships of highly connected data. For example, find similar players, make recommendations, recommend challenges, friendships. You simply build a graph and query through that graph for the connected nature. And for that, Amazon Neptune is a fully managed graph database service. It's easy to build and run applications that need to work with highly connected data sets. Neptune is designed to effectively store, read, and analyze large amounts of highly connected data. You can execute very powerful queries that are easy to write and perform well on connected data using graph languages like Gremlin and Sparkle. Now you can contrast that with traditionally you would have used a SQL database for that in the past. And you would have to use write very complex SQL queries that then become hard to tune, and that would start impacting the performance of your databases. So with graph databases, you reduce a lot of the complexity of your application code that wouldn't otherwise be required to actually get those types of connected relationships and derive meaningful value out of those. So you can build applications like recommendation engines. You leverage graph databases for fraud detection. You can leverage them to build social feeds. And Neptune is built using some of the same technologies as Aurora with decoupled scalable storage, horizontal scaling replicas, and has similarly high availability characteristics. There are two primary graph models that are widely used and can be used with Neptune as well. The first one is the property graph, which is an attributed multi-relational graph, and the leading option that implements that is Apache Tinkerpop. It provides an imperative traversal language called Gremlin that can be used to write traversals on property graphs. And these graphs are very familiar to developers used to relational models because it's just about relating different entities together. They are called vertices in a graph. And the second one is the Resource Description Framework, RDF, which is standardized by W3C, part of the semantic web. Sparkle is the query language for RDF and allows users to express declarative graph queries against RDF graph models. RDF provides flexibility for modeling very complex information domains. So let's see how this can potentially be implemented in a gaming workload. And I have here an example of a recommendation engine graph. You can find more examples at that GitHub link on the slide. So here's how that works. You've got vertices, which are the games or the players. And you can see that on the graph. The green dots are the game vertices, and the red and the blue dots are the players. And you have relationships between them, which are modeled using edges. In this case, in this graph, you know, the relationship is a like. User X likes game Y. And you can use this graph model to actually query for complex recommendations. For example, what games does user X, what games can be recommended to user X that he doesn't already like? And you have on the slide an example query that shows that type of a traversal. Now the query might look a little bit intimidating at first, but when you look at it closely, it's just a traversal of the tree. It starts from the user itself, identifies what the games are that he likes, and then traverses through the nested paths of likes to identify other players and the games that they like, and simply then just catalogs and provides you with a list of results that are essentially the 4 games that weren't identified originally by that player as being liked. So you can use that simply as a recommendation engine. So in summary, you want to use the right solution for the right relevant workload and the scale that you need it for. And we call that polyglot persistence. It's a fairly common term. It means just that you're using the right data store for the right type of data that you're modeling. And you want to leverage the native scaling capabilities that are provided by the AWS database services that you use as much as you can. But that might not always be enough. So it's always useful to supplement that with potentially predictive metrics that help you get ahead of any sort of spikes or demand curve increases. And we've also discussed in more detail 4 database services that are really key for gaming workloads. Amazon Aurora, which help customers deploy high throughput, high concurrency relational workloads. Amazon Dynamodb, which is a highly resilient, high throughput, high performance NoSQL database. Amazon Elasticache, specifically the version for Redis, which allows you to operate Redis in-memory databases really easily on the AWS platform. And Amazon Neptune, which is a graph database allowing you to query and model highly connected data. Thank you so much for joining us. And please feel free to reach out to an AWS expert through the platform if you have any additional questions.